Good morning all of you for today lectures on scours, and most focus I will do on bridge scours. If you know it, whenever we design a bridge over the rivers, the major challenging task comes for us to do a hydraulic design of the bridge. Today we will discuss about how we do the hydraulic design of the bridge, and mostly standard guidelines are which is available from HEC-RS reference manuals as HEC-RS models, and also we will talk about the partly with fluid hydrodynamics books. That is what we are partly following it. Combining these two books, I will summarize it how we do hydraulic designs of a bridge. Before going to hydraulic design of a bridge, this is what we talk about contraction scours, then we will talk about Larson models, how to compute the contraction scours and the abutment scours. This is what today I will cover it. About the wire scours and total scours and countermeasures we will discuss in the next class. So, if you look at when you talk about a bridge, and if you look the figures like this, the scour formations happens. That means the removal of the bed materials, that is what the scour, and you can see the scour holes, and you can see this the flow properties in terms of vortex formations, in terms of the changing the velocity field. So, whenever you have a scour for hole formations, exactly that is what happens during the high flood. During high flood, we have the scour mechanisms in a bridge piers. To protect a bridge piers, we should estimate the scour depth, and we should have a foundations below the scour depth. Then the bridge is protected from the scour hole formations. So, this high flood, in case of the bridge, we consider a design flood. For the design flood, we have to estimate what is the scour hole depth, what is the extent of the scour holes. Like if you look at these cases, if you look at this field photographs with a bridge piers, you can see the scour holes. You can see the scour holes. If you look at the bridge scours, is very important for us, and that is what we design for design flood, and we need to estimate the scour holes. And if you look at these ones, it depends upon the flow characteristics, it depends upon bridge pier characteristics, it also depends upon the bed materials. The same way you can see the scour hole formations when you go for any bridge site, you can see the scour hole formations. Nowadays also it is possible to do the mathematical modelings, CFD modelings, to know it how these scour hole formations happens when you have a 3 piers or consecutive piers are there. It is a quite challenging task to do hydraulic design of a bridge, because if you look at the bridge constructions, the cost of bridge, if it is considered C, that is what is have a proportional to the length of the bridge. More the length of the bridge, the cost will increase it. But same way, if you look at the foundation cost, that is what is have a proportional to the scour depth. So, the foundation cost, it also is a proportional to more the depth you go for the foundations, that depends upon the scour depth, the cost of the foundations is increases. And so, that way we need to have a balancing on these two. So, if you reduce the length, the scour depth is going to increase it, the cost of the foundations is going to increase it. If you do not reduce the length, the cost of the bridge, the span of the bridge will increase it. So, that is the reasons the hydraulic design of the bridge is not a single way to design it, it is an iterative way to design it. You design something, try to find out the cost effective, then again you design it. So, it is a iterative way of design, is a hit and trial methods, find optimization solutions where the total cost of the bridge is minimum. So, that is what, and hydraulically you have to try to look at the safety of the dam during the high extreme floods, where at that period you will have the high scour depth formation at the bridge piers. Same way other component we will talk about. So, the basically the hydraulic design of the bridge is a very interesting fact, and that is the reasons mostly we do the hydraulic designs of bridge. If you look it, it depends upon the flow characteristics, it depends upon the sediment characteristics, also structure intervention. They all are interacting each others. They all are interacting each others. That is what it happens with the flow, sediment and the design structural intervention. The flow, when you talk about the flow characteristics, we talk about during the extreme flood event, the design flood event. It could have a frequency of 1000 years or return periods, or it could have a 10,000 return periods or the 100 years return period. That type of floods, what the flow characteristics at the river locations that interact with the sediment, the bed material sediments, formations of scour holes happens it. That depends upon the structures, what type of piers we have, size of the piers, what the dimensions of the pier or the abutment, all we interacting each others to find out what will be the hydraulic design of this. That is the reasons it is not a easy task. That is the way what you do it. If you have a hydraulic problems, that problems we try to solve by physical river models. We have the plume, we try to put these the piers, scale down models and run different characteristics, flow characteristics and the sediment characteristics, and try to do dimensional analysis and establish the empirical relationship with the scour depth, with the flow characteristics, sediment characteristics and the structure characteristics, like what will be the pier dimensions, the type of the piers, all we decides. That is what we establish a empirical equations. But nowadays river mathematical models also comes to pictures, okay. Taking care of a 3-dimensional river models are there, 2-dimensional models are there. With the sediment transport we can also look at how performs well, but many of the times these are complementary to each other, because physical river models all over the world, the people do the physical river models to do a hydraulic design of a river, because it hydraulic design of a bridge, it's a very much cost expensive. So each bridge we have to have a unique designs. That's the reasons we go for physical river models, but nowadays also the mathematical models are complementary each others. So if you look at that way, we can have a physical river models, dimensional analysis, empirical relationship. That's what is gives. Parallelly also we conduct field measurements, the scour depths, the scour's extent, and also the engineering experience. All these things are integrated. Finally we create a design guidelines for designing the bridge components, the hydraulic designing of bridge components. That is what is that. In summary, what I am saying that whenever you have the bridge problems or any hydraulic problems, we go for physical river models or the mathematical river models, do a dimensional analysis, empirical relationship, integrated with the field measurement and the experience, prepare the design guidelines. These are not, as the technology improves, these design guidelines changes it. This is the basic philosophy of hydraulic design of a bridge or the river training works. Now if you go to the scours, what do you mean by the scours? Okay, as I have shown you graphically, that's what is the erosion of the bed level of a river because of it takes place due to the exclusions of river bed materials, the removal of the bed materials, okay, by the flow of the waters. Okay, that's very basic definitions. What type of scours happens it? One is general scour, contraction scour and the local scours. Whenever we construct the bridge, we contract the floodplain or the river or the both. So, basically what we try to do it that we contract in the floodplain, otherwise we cannot have affordable to give a river space. So because of the contraction, there will be the scour mechanism. This more detail will go it. Because of the contractions, you can try to understand there will be the accelerated zone. Because of reducing the width, the velocity is going to increase it, there will be accelerated zone. And during this breeze path and the channel flow through the breeze, flow over the floodplain are the breeze path and channel through the breeze waterways. So you can see that we contracting the channels. But general scour is that any river, if you know it, the bed material doesn't remain fixed, it changes with the times. That depends upon the basin characteristics, that depends upon changing of the rainfall patterns, changing the land use land covers. That long terms, the change of the bed levels, that is what we call the general scour. The long terms aggradations of the rivers, that is what we do it. If you have a last 100 years of bed level data, we can find out whether the river is aggradation stage or the degradation stage. And based on that, if we know this on average aggradation rate or the degradation rate, and we can quantify it, what could be the long term scour, okay, which will be progressive bed degradations. The progressively bed degradations will be there. For example, it may be 5 centimeter per years, that is a degradation rate. So bed levels are lowering down at the rate of 5 centimeter per years. So if you are designing a bridge for 100 years, then you can compute it what could be the total general scours happens in the next 100 years. So we can have just a simple multiplications, but that needs to have a last historical bed level data to quantify the general scours, where that part we are not going detail here, but contraction scours and the local scours. Okay, that is contraction scour because of contracting the river space in the floodplain as well as in the channel. The local scour, it's developed near the structures due to the obstruction of the flow. That's what it happens. When you construct a bridge pier, when you construct an abutment, it is because of that locally, it changes the velocity field, changes the flow patterns, the vortex patterns and all. Because of that, what is the scour happens, that is what is the local scours. Here we divide the scour in two parts. One is clear water scour, another is live bed scour. The clear water scours in that regions, that there is not a subflight by the approaching flow. The sediment is removed from the scour wall, but not subflight by the approaching flow. That means approaching flow is not carrying any sediment to the scour holes. All the scour materials are going out from the bed near to the local zones. There is no bed sediments are moving it along with the rivers. If moves with along with the rivers, that means live river conditions. That's the condition is live bed scours. There are the bed load is moving it. In that conditions, whenever you have the scour, and that is a continuously fed with the sediment, and that what is make a live bed scour. So clearly understand what is a clear water scour and live bed scour. Now let's go for next one. What it actually happens it? If you look at this river coming with a velocity v1, width is b1, but because of this bridge constructions, we confine the river, we contract the river. So as we contract the rivers, we make a width of the river is b2, okay, and if you look at that, you draw the streamlines, it will be like this. There will be accelerated zone, there will be the scour hole formations here, there will be backout constricts scour will be there, and there is a vortex presence. So if you look at that, the maximum scours will happen to these points, and there will be backwater scour. And if you look at the if I take a section, okay, and this is the H depth of the water is coming, V1 is velocity feed, and this is the original bed levels, okay, and because of these contractions the scour depth is a D max, and this is what our scour hole, the cross sections of the scour hole formations. So the V1 velocity is coming it, H is the depth, and here this D max scour hole is happening. Here it is showing it where the scour hole formations happens it, and where other two scour hole backwater contraction scour also happens at this. This is the structure of the flow panorama. We can get it. You just conduct a lab experiment with a plume. If you just have a contractions points and have the flow, you can easily see these contraction zones. Okay, easily see the scouring zones where the scour happens it, and what could. So the flow velocity through this channel contraction is high due to the directions of the flow area, which is basic things, and that's what is increases the bed shear stress. Okay, that's the reasons. As the flow velocity increases, the bed shear stress is increases. Due to this, scouring of bed materials takes place. That's what we call contraction scours. This is what it happens in bridge, barrage, weir, cross drainage work. Many places we can have a contraction scours. Okay, not only the bridge, you can have in a barrage locations, you can have it the weir or the cross drainage. That so if you look at that point, what it happens in a river when you construct a bridge. As I said that river has one space, and we are designing the river for design flood, maybe 100 years return period flood, maybe 500 return period flood. That means the flow exceeds the channels. Okay, so flow exceeds the channel capacity. Very rough idea is that the bank full discharge of a river is about to 2-year return period discharge. So when you have a 100-year return period discharge, definitely this is the discharge is carried in channel as well as in plot plane. That's the reasons what type of constraint we are doing it. The case 1, the conditions of the contraction scour, where it involves overbank flow on a flood plane being a force back to the man channel by the approaching the bridge. That's what is case 1 conditions. Okay, that's the case 1 conditions. Case 2 is a flow is confined to the main channel. Flow is confining to the main channel. There is no overbank flow. There is no plot plane overbank flow. So the normal reverse canals width becomes narrower than the bridge itself, or bridge size is located at the narrowing ridge. Most of the times we choose a bridge locations which is a narrowing part. That's what I discussed earlier. The cost of the bridge project is proportional to the length of the bridge. So that's the reasons the site selection of a bridge locations we take care of that should have a narrowing locations. The narrowest part of the river we can construct a bridge. That's the, because of that there will be the case 2 is with the flow is confined to the main channel, but the normal reverse channel width becomes narrow due to the bridge itself, or bridge side is located at the narrow ridge. Case 3 is a relief bridge in the overbank area with little and no bed materials transport in the bank. Okay, that's basically clear water scours. Okay, there are the bridge piers will be there, abutment will be there. On the floodplain area, there will be no bed materials transport mechanisms will be there, and that's the case 3, which is a relief bridge conditions where we have a only clear water scours. But the relief bridge over a secondary streams, as you know it cannot have only one main channel, it can have the multiple channels. There could be a secondary streams on the overbank area with a bed material transport as the similar to the case 1. So you can have a different cases of the estimating the scour hole depth, because these are different conditions like a case 1, case 2, case 3, case 4. So that's the bridge design conditions we consider it. So now if you look at the contraction scour, as I discussed earlier, so we will have a live bed contraction scour, clear water contraction scour. Okay. The bed contraction scours occurs when bed material is already being transported into contracted bridge sections from upstream of the approach sections. Okay. That is what I tried to explain you. Water contractions scour, that is a clear water contraction scour, is a bed material sediment transport in uncontracted reach is a negligible or less than the carrying capacity of the flow. Okay. So, this is again we are defining it, what is live bed contraction scour and the clear water contraction scour. Now, if you look at what we defined it, is it a live bed contraction scour or the clear water contraction? We define in terms of a critical velocity, in terms of a critical velocity. The critical velocity being of motions, okay, sediment particles is Vc for the d50 size of the bed materials is calculated and compared with the mean velocity of the field. If the Vc is greater than V, then you will have the clear water contraction scour. If it is less than this, the critical velocity of bed material is less than the mean velocity of our flow, then we have a live bed contraction scour. But now try to look at that, if you have the live bed and clear water contraction scour, how do they vary with time? So, if you plot the time versus the scour depth, if you look at the y-axis scour depth, the clear outer scours will follow this curve, okay, and then it will reach the equilibrium scour depth. Okay. So, with time it will be increases as a power functions and it can reach as a steady level, equilibrium level. That is what is the equilibrium scour depth formations will be there. But in case of live bed, there are the bed sediment materials are coming to the scour holes, again transporting that. What will happen is the scour will accelerated very fast as compared to the clear outer scour. After that, it will have the steadiness, it is a fluctuating over that, as can you understand it, as the sediment particles are coming upstream of these scour holes, that feeding mechanisms are there. So, we cannot get a steady equilibrium, there will be a plus the positive and negative sign, the storage and reductions part will happen it. That is the reasons you will have a scour depth of increase will be there and there will be the fluctuations. So, that way the time average equilibrium of scour depth what we get it, time average we do a scour. So, as this figure indicates for us that the clear water scour is larger than the live bed scours. Okay. Clear water scour is larger than the live bed scours and we define the scour between that. Now, let us compare that the scour, contraction scour also depends upon what is the dimensions in terms of length of contractions and approaching channel width. So, we define it whether it is a long or the short. Gandhinagar has defined it that L1 by V1 ratio, if it is greater than 1, it is a long contractions, and wherever Wavy 1984 consider L1 B1 is greater than 2 will be considered as long contraction scour or otherwise short contraction. So, if you look at that, it also depend upon the length L and the B, L and B1, the length of the contractions and the B1, that will be give us that whether the contractions are long or the short, because the hydrodynamic behaviors or sediment scour hole formations behaviors are changes it as we go for long contraction scour or the short contraction scour. Now, if you look at we have just a simple theoretical models which is a Lorentzian models, okay, which establish a channel contractions as shown in the figures. It is a very simplified cases that V1 you have width, it contract to the B2, it's having the Lth length. As is a constant discharge Q is going it, flow depth is H1 is here. At the scour hole, we have the H2 and we have the ds is the scour depth, and this scour hole can have the depositions of material at these points. Okay, that's it's scoured. Remove these materials also have a depositions near those we are not interested in where it is deposited, but this, as soon as you have the scour hole, there will be the sediment depositions will be there, the downstream of the scour holes. So if you look at this geometry of the channel geometry of the contraction scours, okay, you can have a continuity equations, you can have a energy equations. Okay, so we are applying this energy equations at the two sections. Okay, that's what you know it. And here we have considered the specific energy with the reductions factors. Also we have considered, because of these scour hole formations, there will be the energy losses, which will be the functions of upstream, the u1 velocity and the ut velocity. So velocity had the difference between these two, that's what we take with a multiplications factors. We will get it. What will be the head losses? The energy losses is happens it because of this contraction. There will be formations of vortexes. There will be the high turbulent structures will create it, and that what will have the energy losses. Here we just quantified as a pipe flow is a proportional to the velocity head difference. Okay, velocity head difference, that what will cause us the energy losses. So if I rearrange these equations, I can write in this form, which is very simple form. Okay, and here FR1 stands for the flow proud numbers at the upstream locations at the section A1. So I know these flow proud numbers. If I know the velocities at the 2 point at the velocity at the upstream at the scour holes, we can compute it what will be the ds by h1. So if you know h2 by h1, then we can compute it what will be there. But if you look at this, not that when you look at the scour hole formations, HF is the head loss due to the flow transitions, FR1 is approaching flow proud numbers, KL stands for here head loss coefficients. So mostly we try to look at what is the ratio between H2 by H1, which is not known to us. More detailed derivations I am not giving to here, but if you look at that, I can compute it, the approaching shear stress at the channels, I can compute the tau 0 subscript 01 will be indicating me approaching the shear stress, the base shear stress at the approaching zone and the bed shear stress at the contracting zones, because if I assuming it comes to equilibrium phase, that means I can need the critical shield numbers, shear stress will achieve it. The critical shear stress will achieve when you have the scour hole formations. After that's the equilibrium conditions is achieved when the bed shear stress is equal to the critical shear stress. That's the conditions. If I use it and take care of H2, H1 and all the things, I will have a relationship between H2, H1, and that what if I substitute it and neglecting the loss, the component, okay, that means then we will have a simple relationship between the B1, B2 and shear stress of upstream, critical shear stress, which we can compute from the bed material distributions, and we can compute it what will be the scour depth. So this is that the data what we are computing, just a theoretically considering it's a equilibrium phases. But if you look at that, many authors they did a similar type of experiments and try to modify it. Like for example, Stroff 1932, he has similar equations from the experimental data and try to find out what could be the value is claimed. But Kumar 1966, he has included the particle size distributions. This is for the clear waters and the live bed scour. So, sigma z g stands for geometric standard deviations of particle size distributions. That is the reasons these covariance that it consider the as you know it, this when you go to a rivers, the bed materials are not uniform size. You can have a particle size distribution of the bed materials. From that you can compute the geometric standard deviations of bed materials, and if you know these flow proud numbers and if you know the B2 and B1, you can easily compute the DS values. Okay, that is very easy things that to compute. That means in this Kumar 1966, not going more details, it consider it the mixed distributions of particle size, bed material particle size, to estimate the scour depth, scour hole depth in a contracted zone. So, same way there are lot of studies has been done it. If you look at the Gill 1981, Lim 1993, 98, more the derivations are more or less same, but there are the exponent components is varying for live bed scours, and if you look at then this case there is a D50 is there, the bed materials part is there, and you have the B1, B2, and you have here F1D, it stands for not the flow proud numbers. That is you try to understand, it is not a flow proud numbers because it is in terms of D50, it is not in terms of G. So, that is the way it is a different than the upstream. So, it consider the particle size distributions, it consider particle size distributions. That is what in 93 and 98 also changed, also develop it these simple equations. Only if you know the B1, B2 and H1, you can know it what could be the scour holes. So, that is all these clear waters, the regime conditions like clear water, live bed or clear water or the live bed. Looking that always point is coming it how to estimate the critical flow. Okay, that is a Lorentz models. If a critical velocity over which material size D50 and smaller, then will be transported. Okay, that is in spin motions. Okay, that is will. So, that, and if you have a average flow depth in a man channel or the overbank area, D50 is a 50% finer, D50 bed material value, Ku is value, we can compute the Vc is the critical velocity above which material of D50 and smaller will be transported. So, these are experimental finding, it is with the D50 values and the coefficients. Now, if you look at that, there are the equations which is adopted by US crop of army. They establish in the live bed scours with a very simple formulas in terms of Q1, Q2. Q1 starts for a flow in man channel or plot plane in contracted sections before the scour. Q2 is a flow in man channel plot plane at this contracted section, which is a transporting the sediment, okay, which is the transporting the sediment, and W1 is the bottom width of this man channel, the plot plane approaching sections. W2 is the bottom width of the man channels of the plot plane at the contracted section, the less the pier width, which approximately the top width of the active channel. So, that way if you look at that, there are simple equations are there, which in terms of Y1, in terms of Q2, Q1 and W2, only the K1 constants are there, the power exponent is there. Otherwise, we can compute what will be the these simple Lorentz models as is given with a ratios. Okay. If you look at these are all are non-dimensional ratios, and their exponent is we are estimating from experimental data set. Now, how to get the K1 values? Okay. If you look at this, K1 is exponent of the mode of the bed materials. Bed can have a material type, mostly contacted bed materials, some suspended bed materials discharge, mostly suspended bed materials. So, as we go for this ratio, okay, increases, the bed materials and the suspended material behaviors are changes. Okay. Like when you have this value is lesser than 0.5, if you look at this K1 is 0.959, it's a mostly a contacted bed material. The river will have a, the bed sediment what will transport as a bed load, it will transport it. But when you in the transitions of 0.5 to 2.0, we will have this K value, this is means suspended bed material discharge. Then we have a mostly suspended bed. The V star we can compute it, which is a shear velocity in the man channel or the plot plan. That's what will be the function of the slope of energy gradient, acceleration due to gravity and the fall velocity. These are experimental finding. We don't have a much physical concept to define it, but you try to always understand it. When you talk about the scouring mechanisms, it is a flow, interact with the sediment transport and the structures. These are three combinations, three interaction between flow, sediment and structures. That's the reasons after conducting a series of the experiment, we get empirical equations. We may not have a physical justification for these equations, but we can try to interpret it and make it a design guideline or design skill. So, what type of transport mechanisms should be there in the river and what type of value should go it beside the numerical value. That is the reasons whenever you design a bridge, field visits is necessary to understand the rivers, not only the numerical values. Okay, that is the more points to that. When you have a clear water contraction scours, okay, which is Lawrence in 1963, which gives in terms of median diameters of the bed materials. C is a constant which is 40 per metric units, and you know this Q values and W2 values. And see, if a bridge opening have the overbank area, then separate contraction scour is computed for main channel, each of the overbanks. So, you can understand it, the channel, you can have the abutment either in a main channel or in the overbank or the floodplain area. That the understanding we should have. Let us come back to the scour at the bridge abutments. You know it, the abutment will be there in a bridge, and what are the scour happens in the bridge abutment locations. And if you try to understand the flow behaviors, if I have the left bank or the right bank abutment, as the flow is coming from this distance, and there will be the stagnation point will be there, and because of that there will be change of the velocity as the upstream flow is having the higher velocity at the pre-surface, at it reaches to the abutment, that velocity reduced to 0. Okay. So, that is the reasons there will be the downflow. Okay, there will be downflow, and this downflow will start eroding the bed materials. As they start bed material eroding it, and it make a scour hole formation starts. As the scour hole formation starts, because of the scour hole formations, there are horseshoe vortexes formations are also happen, which is called primary vortex. And the parallelly also the secondary vortex will be formations, and just above behind of this abutment you can have a wake vortexes formations will be there. At the surface you can have a bow vortexes. If you look at that how the flow structures are changes when you have the flow near to an abutment. How the flow structures are changing? It's there will be downflow, there will be formations of horseshoe vortexes, there will be secondary vortexes, the wake vortex formations, bow vortex formation, and the scour holes. Now the same approach will go it discuss it here, that conducting a series of experimental studies or the field measurements, establish the empirical equations, and that what is validate for the bridge which is already constructed, they validate the scour depth. So the basically is that's what again have to 72% damage, abutment damage involved in 383 bridge failures. So bridge failures it so often happens because of damage at the abutment. So you need to design the float plate which is abutment is too complex due to there is a three-dimensional vortex around the structures. That's what I try to show you. There's three-dimensional vortex structures what it happens it. Now if you look at that, there is a primary vortex, that is a horseshoe type of vortex is happens, which is the where is the downflow mechanisms happens. That's what is that primary vortex will be there. It will be elliptical in shape with a inner core regions with a force vortex and outer core regions as a free vortex. You can try to understand it. How this vortex is complex, that it will be elliptical shapes with the inner core regions will be force vortex, the outer core regions will be the free vortex, as you know from the fluid mechanics book. The secondary vortex will be developed at the next to the primary vortex, which is the counterclocks directions to the primary vortex if you look at the secondary vortex. At the downstream of abutment, the wake vortices that create the flow separations at the upstreams and the downstream of. So you can have a wake vortexes formation. So this is a three-dimensional very complex flow structures happens near to the abutment. So looking that we can compute the scour mechanisms as a live bed scour. The scouring mechanisms at the an abutment, it also depends upon the obstruction of the flow forms a horizontal vortex, okay, and the running along these two of the abutment that forms a vertical wake vortex at the downstream. That's what we are talking about, how the vortex formations happens it. And the weighted embankment length, this L is greater than 25 divided by the approach length, or the embankment weighted embankment length is 25 times than the approaching flow depth. Then we use the higher equations. When this weighted embankment length is lesser than, then we use the four Leach equations. We use 4 Leach equations, which is 90s Richardson's equations and all. So these are if you look at basic way, this is what the higher equations which is developed from the field data scour at the end of the spurs. The spur at the abutment is more or less same for the Mississippi rivers by US Association of Civil Engineering. That's what it developed from the field data, the scour data. The scour depth in a feet, y is upstream flow, will have the functions of upstream flow Proud numbers. K1 is a correction factor, K2 is a correction factor, Y1, and this is what is developed using the higher equations. And the K1 is, if you look at that, K1 depends upon the type of abutment. Is it a vertical wall abutment? It's a or vertical wall abutment with wing walls or spill through the abutment. This is, it depends upon what is the abutment type. It is a vertical abutment, the value is 1. That means it's a more. And when you go for a spill through abutment, you will have a 0.55, which that's what this value becomes 1. So in case of same abutment, if you change it from spill through abutment to the vertical abutment, the more or less 2 times the scour hole depth will be there because of abutment. So that's the engineering skill where we try to understand it, how the K1, K2 it changes it, because we know the flow depth which we cannot change it. We know the upstream flow depth for a design plot. That's what we can change it. We can change it as a hydraulic designers, the K1 value or the K2 value. That's what we look at by understanding from these tables, like what type of structure we should construct, what type of abutment we should construct, whether the vertical wall abutment or the spill through the abutment. The spill through abutment will have a less scour, almost half of the scour of vertical wall abutment, or we will have a vertical well abutment with the wing walls will be 0.82. So what my point is to highlight is here is that when you look at the scour equations, that's what is the knowledge for us, and that gives a hint for us how should we design a abutment with minimum scours. That's the way, because try to look at that the scour depth should be minimum, otherwise the foundation cost will going to increase it. That's what and if you look at this K2 variations, the K2 is depend upon, most of the times we tried that the abutment should have the perpendicular to the river flow, but it doesn't happen it. That is the 30 theta equal to 90 degrees. So you will have abutment, but many of the cases you will have a theta angles, okay, the embankment pointing towards downwards or the upwards. So K2 is a function of the theta by 90, and if you plot the K2 value becomes like that. That's the reasons the angle between theta is meter slot, which is the angle between the attack. If you have the flow angle between the attack, whether the pointing towards downstream upstreams, the K2 value is changes it, and that's what is value is increases from as close to 0 to 1.1. So we try to look at that how the alignment of the abutment we should consider it. Please be noted it, we are looking for extreme plot or design plot conditions. That's the reasons we need to have a physical models, try to understand it, what would be the hydraulic conditions at design plot conditions, which as you know it is a rare event and we cannot observe that data. So that's the reasons we follow physical models or the mathematical models to estimate the hydrodynamic behaviors, and then we try to look at what could be the scour hole formations. So that what we do it, it's a combination of physical modeling, mathematical modeling, and these empirical equations all gives us to develop a models, design a bridge components which will have a minimum scour depth. With this, let I conclude this lecture.